Okay. Good evening, everybody. I hope you're well and happy and healthy. And I'm welcoming you to, I think it's the third lecture within the lecture series Hallo Biologie, which we do as part of the Artificial Nature Seminar in TU Berlin in a collaboration with Mansoura University. And it's also part of the DAAD exchange project, and we are very happy to welcome you to tonight's lecture, which is by Professor Carola Diris. Professor Diris will talk about designing matter granular architecture, or better, designing matter granular architectures, possibly. Let me briefly welcome and introduce Professor Diris to everybody. Carola Diris is a professor of material code at the Weissensee School of Art and Design, Berlin, with the Excellence Cluster Matters of Activity, MOA, at the Humboldt University zu Berlin. She has been conferred her doctoral degree with distinction from the University of Stuttgart in 2019. Previously, Professor Diris has studied at the Architectural Association in London, the Swiss Federal Institute of Technology, the ETH, and the Technical University of Brunswick. Teaching engagements included the Architectural Association, the Städteschule architecture class, SAC in Frankfurt, and the ICD, the Institute for Computational Design and Construction in Stuttgart. At the Institute for Computational Design and Construction, Carola Diris has conducted research on granular architectures, where she has designed granular materials in architecture. She has been engaged in transdisciplinary research, collaborating nationally and internationally, among others, with the Institute of Multiscale Simulation, Friedrich Alexander University in Erlangen-Nuremberg, Germany, and the Beringer Lab and Duke University in the United States. Professor Diris has published numerous articles in her field and lectured both within Europe and the US. Her research on designed granular materials has been recognized with the Holcomb Acknowledgement Award Europe in 2014 already, and the Material Prize Acknowledgement Study and Vision in 2019. Selected works have been included in the traveling exhibition Hello Robot that started in 2017 at the Vitra Design Museum, Germany, and the opening exhibition Minding the Digital of the Design Society in Shenzhen, China. Carola, a very warm welcome to you. Thank you very much for joining us, for taking some of your precious time to share your work and your research. And the stage is yours, and we're looking very much forward to your talk. Thank you for coming tonight.
Yes, thank you, Liz, for the wonderful introduction, and thank you for having me. It's an honor to be here, really. So I think I will go ahead and share my screen. Second. So everybody can see my screen well?
Yeah,
yes, all is good. Okay, so my talk is designing matter, granular architectures. And it is indeed a plural, because obviously looking at the architectures of, you can see this is a simulation of a granular material. And with architecture, one might as well consider the design, the architecture of the grain itself, as well as the immersion forms that it allows to produce. So I'll give a brief overview of my talk. I'll first introduce the notion of design, granular materials, and architecture. I'll show you two of mine at the ICD in Stuttgart, and then also include my teaching research, because my work has always been wonderfully accompanied, I would say, by very excellent students. And then I'll show a little bit of current research and an outlook. So what is designing matter? When we design matter, what we do is we look at what might also be called the material code, the actual embedded intelligence of a material. So we first analyze it and try to understand it. So to speak, we listen to the material. On the right-hand side here, you see a granular material which is investigated with photoelastic techniques, which allow to see the force lines in the material itself. And I would call that a form of a material code. What we then do, we encode the material. So what you see here on the right is a test that I did with the Beringer lab in the US, where we started to change the form of the particles into crosses, and thus the force lines flow differently. For example, more linear and more stable interconnections when compressed. And this whole research is embedded in the field of designed materials or designed matter or designer matter. There are many little variations of the word, but in the end, they all mean the same. They mean the interrelation of form and function in a material. And what that denotes is, on the one hand, to find the function for a given form, but also to find a form for a desired function, which is what you see on this slide here, which is an inverse optimization of a granular material done by simulation. So you set a certain desired packing density for a granular material, you run the simulations, and you optimize the particle shape for that. That's a very advanced field of study, and we would need granular physicists for that. Now, we are architects, and very passionately so, and we should wonder, why do we need designed granular materials in architecture? Now, usually we don't build on sand, and much less do we build with sand. First, let's understand what is sand. Sand is a large assembly, a large number of particles in loose frictional contact. And what we do when we design the individual particle, we start to calibrate and tailor the overall behavior of that material. Now, why is that important and very different in architecture? So we know in architecture, we are very used to placing and precisely defining both the individual element and the overall geometry of a building. A brick building is one of the most prominent examples of that. And when we work with sand or granular materials, we actually can only pour the material. It starts to behave in a certain way, and we need to observe its emergent properties. In a more down-to-earth approach, we would also want to ask, what does it give to the construction industry? And I've put this slide because I think it shows pretty much the mentality of construction at the moment. We put things in place with much energy and effort, only to tear it down after a couple of years, after, 40 years, 60 years, 90 years, the whole thing gets destroyed. And now with granular materials, you can reuse the very same material again and again. The formation on the left uses the exact same sand as the formation on the right. Overmore, and that's a more subtle observation, granular materials have the possibility to adapt. So they are very finely calibrated with environmental forces, such as in this case an airflow, and they take the formation, they start to interact with that force of wind flow. So they are at the same time very humble and very intelligent materials. And now lastly, what we do is when we design the granular material, I've already hinted towards that, we design the behavior of a material. So this still demo video shows it, and I'm not going to speak, I'm just going to let you watch it. So this is what designed granular materials do. Now, in my research, I have focused on using designed granular materials for large-scale architectural construction. My aim and my proof of concept was, can we really build full-scale structures with granular materials where the individual elements are designed for specific behaviors. Obviously, there were some precedents. On the left-hand side, you see very relevant work by Eiichi Matsuda conducted at the Architectural Association that studied on a model scale. And on the right-hand side, there's one example from granular physics where one finds a wide range of particle shapes. So we've obviously always investigated or looked both at architecture and granular physics because for this project, these fields are very related. And there were several projects in architecture, yet they didn't really go to full scale so far. And there are many projects in granular physics which investigate a wide variety of particle shapes, yet there was no coherent system investigating them, except for maybe the one on the second row, third from the left. They started to establish quite a good system. And certainly there was no interface with architecture. We used both computational and analog methods for that. So on the left-hand side, you see a physical experiment. On the right-hand side, you see a so-called discrete element simulation. And this discrete element simulation allows to X-ray through the material and, for example, look at contact points in the material. And that's a very useful type of investigating, for example, stability, compressive strengths, and so forth. Now, I've built two prototypes in my time in Stuttgart, the ICD Aggregate Pavilion 2015 and 2018, and I will speak about the development of both of them. The ICD Aggregate Pavilion is the first of its kind, and it uses the ability of a granular material to form stable columns and vertical angles if hexapods or highly non-convex particles are used. Just to remind you, for a granular material, that's a real achievement because usually it has an angle of repose. So that's radical, even though for an architect it might seem very simple, but for a granular material to form a straight wall is quite an achievement. So the first step was obviously being in a computational design chair to develop a parametric model that allowed to quantify the material by varying the parameters. That's what we do as computational designers. I did packing tests, for example. These needed to be repeated 20 times because it's a material with a high statistical variation. So any result, in a way, needs to be verified by multiple probes. This was also published in collaboration with physicists, which again took the work to another level. These types of studies directly inform the fabrication methods. Obviously, the packing density is an interesting factor when calculating cost. The result of the overall study was that, in a way, varying arm length is more efficient than varying arm amount and also cheaper. This was complemented also by compression tests. One can say very generally that denser packing materials form stronger material assemblies than looser packing ones, which you see on the top. And these compressive strength tests were also simulated and compared to the contact points in the material. So one can also say the higher the number of contact points, the stronger the material becomes. So this is a close-up of two materials, the hexapods and the tetrapods that are used for the simulations. Then after this sort of small-scale investigation, 3 molds were cut, 3 injection molds were cut. And with those, we were able to produce up to, I think, 3,000 particles per hour. So the whole project was taken to an industrial level. On the side, we also investigated forms. We investigated many, many forms, but I settled on the columns. as the most simple installment of the system. And we tested the aspect ratio, so the ratio of the width to the height. And in the end, we settled for the most stable one, which was the aspect ratio 2.5. These decisions are mostly driven by the fact that we build outside. And when you build outside in the public domain, one doesn't want to take the risk of like this incident happening or that incident happening or the structure not holding up at all. So it's a low risk implementation that we took. So then many particles were fabricated. I think by now I have 70,000, which are stored in Berlin. By now, no more in Stuttgart. And in this first installation, we made 25,000 of the whole batch. The particles were distributed by a cable-driven parallel robot. Now, the robot is a story in itself. It's a self-made robot, which two of my colleagues made. And in this case, it was installed outside between 4 trees. It's the right kind of tool to use for that because it allows a large building space, which, for example, a 6-axis robot, it can have it, but it's much harder to install the 6-axis robot in a way that it can have a wide building space. And the tasks that are required for granular materials are not very complex. So the intricate motions of a 6-axis arm are not really needed. You only need to pick and drop aggregates, which you can see here. A little downside is that this specific cable-driven parallel robot wasn't very strong. So the amount of particles that could be lifted wasn't very high. So the columns that we made were installed outside. I have to say that they were done manually, and the tests with the cable-driven parallel robot were done really as tests, how it could work on site. For the matter of speed and for the matter of height, we did the bigger installation with our own hands. And just a couple of numbers, column weighs roughly 95 to 130 kilograms. And has about 3,000 particles in it. So this installation was in a way a very simple one. It didn't have any spatial articulation nor any intricacy of the granular material. Pretty much the same granular material was used throughout. So the follow-up pavilion challenged that a bit and aimed for an enclosed space and also worked with 2 different types of granular materials. One that could flow and one that was stable. So this is the prototype of that. The entire project was preceded by basic studies of how an arch could be formed, and the formwork was the biggest question. And what we observed in this study, which I still like very much in its entire messiness, was that actually something that behaves a little bit like a particle on the bottom right is quite successful. So in a way, if particles flow out of particles, the structures seem to be very stable. In the end, obviously, when one cleans it up, one has this nice arch, which you may have seen before. And we also tested if that principle of using boxes as formwork can be used as a basic mode of forming a dome, which is this dome seen from the inside. And in a way, we just refined the boxes. We just came up with a principle that was as good as the boxes, but maybe a little bit more grainy, a bit more granulary, and we used spheres as a formwork for hexapods. So the spheres flow out, and the hexapods interlock to form a stable arch or dome. This was again tested in a statistical repetition, and all of the arches that we did remained standing. What was pretty important is this little stuff that you see on the bottom. So we were pouring on top of a granular material on gravel, which gives actually the friction so that the arch doesn't bend to the outside. Again, obviously simulations were done. Hexapods surely have more contact points than spheres, which is one of the explanations why they are more stable. And this is the close-up of the force contacts. Now, even more hexapods were formed. The ones from the previous pavilion were reused, and we added another roughly 50,000 hexapods, and we bought lots and lots of balloons, which was great fun. Now the hexapods were stored in boxes, and the boxes were used as the effector on our cable-driven parallel robot. And the robot was installed in an industrial hall, which became a construction plant. And the particles were dropped directly from the boxes. So in a way, the storage system, the effector, and also the formwork for the entire structure become one. It's an entire construction loop also on that end. The pavilion was constructed in layers, so it can also be considered in some ways as 3D printing. And we really did everything with a robot, this time no manual work, except, which I think I will show later, the adjustments of the balloons. And we pre-designed the structure with an inner space, which was removable, and an outer space, which was stable. We also mapped, obviously, the way that the structure was made, and different degrees of density were achieved. Small adjustments had to be made in the layout pattern. This is the way that the basic layout pattern that the cable-driven parallel robot was able to make. So it went from the inside out, and then again from the outside in terms of the spheres. And this is what I meant. We also scanned the entire process with an image scanning technique. So once a layer was made, we scanned which balloons were outliers, and they were moved inside. This scanning and interacting with the structure is a very interesting process when working with aggregates, because this way you can start to also embed maybe different models of interacting with the material, which is more taking account of its emergent behavior. So in this specific project, we went for a finite end geometry, the double dome, but we might as well also go towards the towards an emergent geometry, so where we always interact with whatever however the material behaves, so that the actual end result is not foreseen. That would be a very interesting project for the next installation. Now, this pavilion obviously achieved an enclosed space, so it's a big advancement from the previous one. It has about 20,000 millimeters of production path length, and it has about 70,000 particles of the hexapods and another 50,000 of smaller ones that we used. So it's a pretty big structure. And if you compare the two, you can see that from the left to the right, we moved from a vertical to an enclosed structure, and we worked on the left-hand side with only one granular material, on the right-hand side with two granular materials. So level of complexity was rising. Now, as I said, we also worked with a wonderful group of students in the Integrative Technologies and Architectural Design Research Program. And I'll just show you a little bit what they did, because I think it was very enriching for the entire research. The first one was by Desislava and Angelova, who investigated luminance patterns. So she looked at the way that the granular materials filter light. She did daylight studies and then started to translate those daylight studies into luminance patterns using a specific code in Photoshop, I think. This is the formula to translate the photo into the specific luminance pattern. And then she programmed a robot to interact with that luminance pattern to achieve a specific target luminance. So this is the animation of how the robot did it. By 2021, it probably looks a bit simple, but that was 2014, very early days. And it was a great achievement of hers to be able to actually get the robot to pick specific particles. The entire project was then aimed at building a dome with varying luminance patterns. The next project that I'll show is by Gergana Rusinova. She used simulations in order to assess whether a structure would remain stable or not. Again, those simulations had to be repeated 20 times each for statistical stability. And she linked a pneumatic formwork to a computer, which was driven by the simulations, and thereby could predict whether a structure would fall or collapse, and then the balloons would inflate or deflate, depending on whether a dome would be successful or not. So that's a very intelligent interaction loop. Her next step would have been to use sensors on the balloons themselves. And now the last student project that I'm showing is by Matthias Helmreich, who developed shape-changing particles. And those are highly interesting. So you've seen in the demo videos how much the behavior of a granular material changes depending on the shape. And now what he has done with his hygroscopic material is he has embedded two different behaviors, at least two different behaviors in the granular material. So when the relative humidity is very high, it's a stick. And when it gets lower, the particle becomes so-called double non-convex, so it can hook and interlace. These processes are observed with hygrometers and humidity control sensors, and there's a special lamination technique used for the hygroscopic material. And this is what you get. You get many different wonderful shapes, which inflate almost like sponges, and which you can pick up as one big piece. He obviously observed different walls and how they rise and fall. In the end, he also had some funny domes, almost like a hedgehog forming. So the trick here was how to lay out the particles so that the granular material can behave in a certain way. And his final quite successful project used different layout patterns in order to form a bifurcating wall. So in a way here, the material itself becomes a machine. It moves from one state to the other, thus interlocking itself with its neighbors. And now this leads to our current research and the outlook that I would like to give on the field right now. The so-called granular materials, autonomous granular materials in architecture. So here we work with bimetals, and that was a project supported by the University of Stuttgart. And in a way, what we try to do here is taking up from Matthias to move from a hexapod to a sphere, or more generally speaking, from a non-convex to a convex shape. And we aim to do so either through passive or actively controlled materials. So we would embed two behaviors in one and the same material. We started to look at bimetals and did physical experiments and simulations for those. Obviously, we started to try very different shapes, which I will show you now. The so-called orange or the thistle, so quite complex shapes, and we hope that they would interlock. We used a specific bimetal with magnesium, copper, iron, and nickel. So that was the big advantage towards the wood was that it's off the staple material, so we could just buy it and test it. Yet our intricate shapes were not so terribly successful at interlocking. So I'm just showing you some of the simulations. But these in the test didn't really interlock as much as we had hoped for. They were flowing apart. So in the end, we arrived at a very simple ring that is pretty much what you would have seen in the hygroscopic material. And that is a very successful way of having an interlocking material in the one state and a flowing one on the other. We obviously tested different ways of interlocking the particles, and then in the end assembled 6,000 so-called single particles and 5,000 assembled ones with granular materials. The trick is always to make many, 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 as you know, and in this case, we really had to do them on our own. We had no machines. And then we tested different mixes, which was great fun. On the one hand, single particles, assembled particles, and mixed particles, and we wanted to see which ones interlock better. So after the cooling phase, one can really take those pieces out of the mold. They become entirely solid, which is very interesting. And again, those were repeated 10 times. That's one thing to know. Granular materials, you always need to do many, many repetitions. So in the end, we were able to assemble a structure which was entirely able to hang on its own, which was also comparatively thin. If you look at the thick-walled pavilions before, so this one had only 6 to 15 centimeters thickness. And we could actually also really disassemble it entirely just with a heat gun, which is quite cool, I think. So you've got a material that you can kind of melt away. That is Varya doing it, my fabulous assistant. And yeah, the final dimensions of the structures were 3.20 meters in width and 1 meter in depth. It is quite small, I would say, and very expensive for that. But so far, the most successful structure that we've done in terms of shape-changing materials. So, and I do think that those shape-changing materials are quite promising in terms of a future development of granular materials because they can really embed multiple properties in just one and the same material. So yeah, with that, I would like to close it and thank you. And I'm open for questions.
Thank you very much, Carola, for sharing your projects or the projects of you and your team with us. I'm sure there are several questions from the students and from the audience for you, and I have a few questions and points as well that I'm very interested in hearing your answers or thoughts. But let's do the students first to ask some questions because you're really here to engage with the work and the research of Professor Diris. Omar, you can speak, Omar. You're muted.
Yeah, I have a question, please. A question for hexabots. Yeah. You said you have tested it for collapsing or any problems for collapsing. Does it work with earthquakes, right?
With earthquakes?
Yeah.
I wouldn't test it on earthquakes. I think there's a whole field on seismic behavior and granular materials, and that's actually very intricate. There's specific types of sand that become liquid under specific vibrations.
Yeah.
And that's a whole different science in itself.
Yeah, and for the environmental case, you have said that it's good for solar radiation, and what for the air ventilation? Does this hexapods do air ventilation?
Yes, I think it would ventilate air, but I don't think, I mean, that's a different test. As you've seen, we've done luminance tests.
Yeah.
Yeah.
Okay, and for the AG materials at the last project, if it's in a variable climate, so in the summer it's very hot, and it's in the winter it's very cold. So maybe it will collapse, right?
That's an aspect. I mean, that the reaction temperature was very high in those. I think it was, if I remember correctly, up to 300 degrees Celsius. I have to look at the material data sheet again, which I have here. But yes, that's true. One has to take in account the occurring temperature ranges on site. I think, though, that's less of a problem than the sheer expense of the material.
Yeah. Okay. Thank you so much for your presentation.
Ralph?
Hi. Yeah, thank you, first of all. It was really impressive work, really cool to see. Also the amount of effort that went into that computationally, but also manufacturing all these different pieces. I'm curious, so first of all, I think it's so interesting, the additive manufacturing aspect to this. Like, I've seen 3D printing cable robots before, but I haven't seen any robot that picks up stuff and then drops it. But what I'm most curious about, is about the simulations. So you mentioned that you were doing simulations with different particles prior to manufacturing them. And I'm curious in practice how close the simulation results were to the actual behavior of the material, if there was any large differences. And then maybe also, apart from the contact point metrics, if there were other metrics from the simulation that were useful. Thank you.
I mean, I worked only with the contact points because that's, that's the easiest, let's say. And I'm not a professional simulator, so to speak. But the behavior in the simulation is very close to the experiments. By now, these discrete element simulations are very well rounded. Not so much when the numbers get very high. I think then people say that there's a bit of an unexpectancy in there. But I've never gone that far. I mean, there's different people who go there, not me.
Sure. Thank you. But I mean, so just the simulations themselves were actually useful in terms of informing the design decisions down the line, like.
No, in my case, not. It was a retroactive investigation. The simulation that I've shown for inverse modeling with the spheres, that was actually informing the design. So there they first simulated and then they made the design, which is the much better approach. That's one of the routes definitely that I will take now. But then, that also depends on the growing skill level as a PhD. So I was comfortable with the simulations by the end of my PhD and not in the beginning. So then, you don't really use it.
Thank you so much.
You're welcome.
Do we have, I'm sure there's a lot more questions. And also I would like to welcome the students of Carola Dearis. I think we have some of you students here as well. At least there's some names that I don't know. So I would think that some of them are possibly your students. You will hear from them probably. Mohammed, you have a question. Please go ahead.
Thank you for presentation. I think we have a more application about this hexagonic shape in use as a wave breaker on coasts to like prevent or prevent from coasts from erosion and beaches from making erosion, because these shapes are very cohesion force, so it can prevent the beaches from erosion in the coasts. So we use it as a large concrete shapes. So I asked about the effect of material and size of these shapes on each structurally or strengths. Do you try another material in these shapes, or another
yeah, the strength of the sorry, I didn't want to interrupt you. But were you finished?
Yeah, I'm finished. About the size and the material.
I mean, you also have to take the volume into account that you're working with. So the size always needs to be seen in relation to volume, the volume that you're trying to fill, and then the amount of contact points that you get. So the more contact points you have, the better it is. In a way, then actually smaller particles are sometimes the smarter route to go, because it gives you more contact points. And then again, also longer arms are smarter to go because it gives you more contact points. Yeah, that's how it works. It's a little bit of a relational logic. Does that answer your question?
Yeah.
Kind of.
Okay.
Thank you very much.
Thank you.
Okay, now it's my turn. I just sort of claim that here. I have some questions which are on one hand I'm interested in, but on the other hand also are I think relevant in my teaching or in the learning of the students when dealing with computational design and also how to deal with what they actually create. So this question is now, these two questions are more like for the student body here. First question: what do you think, or how do you deal with the relevance of the drawing? Right, we've seen a few drawings which are surely done differently or came out of a different process than we did this like before scripting and so forth. But is that, do you think that's still relevant? I mean, to understand what the structure is going to be like, or what the space will offer?
I think that touches a little bit on this topic of do you treat it as an emergent material, or do you treat it as a predefined material? And in my two projects, I think I've dealt with it as a predefined entity. I've had, I mean, the columns and the dome, that's not such a surprising geometry. It's just something that we know works well under compression. But I would obviously find it much more interesting to come up with a rule-based system where you can start to actually let the geometry evolve. That's much more in line with what the granular material is. At that stage of the project, I felt, no, it's better to make the proof, yes, we can build with it, and great, we achieve it. But further projects would definitely more go towards this emergent behavior. And then the whole idea of drawing becomes a new concept.
Mm-hmm. Thank you very much. And how do you deal with data management? Because we have always this discussion about, you know, how to label the files, how to do the folder structure, how to make it repeatable. Which in many projects, the projects are so interesting and students are so engaged that the data management or documentation become, it's a little bit on the lower end of the fun priorities, let's say that. Have you figured out like a trick to how to do this?
Yeah, we have that also on the low bottom end of our list.
Yeah, that as well, yeah.
It basically evolved around basically myself having a data backup routine every night. And I mean, that sounds very crafty, but I for every project, I come up with a data backup routine and a data folder structure. And then I implement it mostly myself. I mean, now I'm running the first project in Weißensee with students where they are in charge of the data management, and I'll look at it once it's done. But yeah, we'll see how that goes. I mean, at the institutes that I work at, there's obviously also this whole culture of publication in scientific journals, and then the routine is much stricter. And for that, we need to file our results and make them accessible. And there's specific folder structure and depending on the institute, also a specific instruction manual for that.
Yeah, we have that at TU Berlin as well. It's just sometimes it becomes extremely hard to implement that within the architecture discipline in comparison to the physics, for instance. And I think Ralph is coming from the physics department, so he probably knows. But the more interesting question is the difference between hardware and software. So where do these, how would you define where these two things merge? Because especially in the hygroscopic materials and also in the almost like a flocking behavior or interlocking behavior of the spicules, the hexapods, it becomes kind of, it sort of merges. And how do you speak about this? I mean, what is your definition of that? Because I would say it's becoming the same, but then you have like the natural scientists who say, no, never, ever. And the unconventional computation says, yes, of course. And I mean, I personally claim that there's no analog and digital because everything is digital. So how do you speak about these things?
I mean, I think I'm more on the natural science side of things. That's also the type of discourse I've tried to embed myself in. So I would say no, it is not programmed. There's this whole discourse on programmed materials. I would open the discourse a bit with the shape-changing materials. Because I find them radically different from other materials in the sense that you can really, in that sense, program the material to behave in relation to certain environmental impulses, the heat, the humidity. And then, yes, maybe it's a mini computer. I can follow that argument. I've introduced in the beginning of the lecture the notion of code. That's a little bit of a different thing again. I mean, a code is more like a sign system or a system of inscribing something. And I could go down that route. I mean, if I would say it's a coded material, coded for certain behaviors. Yeah. But I've kind of started to really appreciate the notion of a designed material. It's also quite broad.
I find that just very interesting because the discussions around this and also the terminology is just becoming very complex. And if you don't know the definitions of your conversation partner, it's extremely hard to come up with like a conversation, in fact, about the subject. And so this is also what I'm trying to do with the students to first, understand or define what is code, what is information, what does material mean. And you quoted Sanford Quinter, which I'm very grateful for, 2003, a great time. Wonderful, thank you so much. And is there like a last question from the audience here? Otherwise, I would say thank you to Carola. Do we have? Doesn't seem, no. Okay, this is great. And you are in Berlin at the moment. This is wonderful. I'm in Berlin as well. And
Yes.
I also saw that the matters of activity is in the physics NFTI a project, and it would be great to exchange at one stage.
Yes, it would be wonderful to meet. Let's be in
what-
touch. Let's be in touch. Yes.
Wonderful. Thank you so much. Thank you for everybody who listened and who joined in the conversation. We will have a discussion about this within the artificial natures, and I think also in the design studio. So thank you very much. Have a wonderful evening, and thanks for sharing your work again. And see you soon.
Yeah, thank you. Thank you so much for having me, and speak soon. Bye-bye.
Bye-bye.